Hello, everybody. I'm Zifeng Wang, a PhD student from Northeastern University, the Center for Signal Processing, Imaging, Reasoning, and Learning. Today, I'm going to introduce my paper, Open World Class Discovery with Kernel Networks. Let me start with a very simple example. This is a neural network classifier trained to classify dogs and cats. The normal setting we always encounter is that we got only dogs and cats in both training and test sets. This is called the closed world assumption. That is to say, the class distribution in both training and test sets are the same. However, in practice, there might be outliers in the test set. Say if there's an apple in test set in addition to dog and cats, what if we feed the apple into the trained neural network? It will be classified as either dog or cat, which is not what we want. In order to address this issue, novelty detection methods have been proposed. I'll just take a simple example here. After we gather prediction results from the neural network, we can validate the prediction using a novelty detector so that the low confidence predictions will be classified as novel class. In our paper, we want to go beyond novelty detection, which is formalized as open world class discovery. To be specific, we got a training set of labeled old classes and the test set of unlabeled new classes. Note that this is a simplified assumption as we assume there is no old classes in the test set. In practice, we can always apply a novelty detection method in advance to filter out the old classes in the test. And the final goal here is to train the classifier on the training set and discover new classes from the test set by somehow adjusting the neural network classifier we trained. By discover, we mean grouping or clustering samples from the same new classes. We can evaluate the performance using any of the clustering metrics. So here, we also want to emphasize the difference between open world class discovery and the normal semi-supervised learning scheme. Really, the open world class discovery learning is a new paradigm, as we're dealing with new classes that are never seen in the training set. While in semi-supervised learning setting, although we have this kind of labeled and unlabeled data in the training, there's no new class in the test. So our problem setting is kind of more challenging. And one of the greatest challenges we face in the open world class discovery setting is called knowledge transfer, which means the network trained on old classes generalize poorly on new classes. Let's use our toy example again. Say we have trained our neural network on the old classes containing only dog and cats. Then a simple and intuitive idea is to apply the trained feature extractor. So note that here we're using a feature extractor trained on old classes by removing the last layer from the neural network classifier. So we got the feature extractor and we feed the test set into it, got the feature vectors, and we just apply our favorite clustering method like k-means to figure out the new classes. However, the performance may not be good, although it's very intuitive to do so. That is just because of the poor generalization ability of the neural network trained on old classes. Because the feature vectors extracted from the test set may not be well separated or aligned with their cluster assignments. Thus, we need an approach to address this issue. That's why we have our method. So our contribution is as follows. We proposed a novel HSIC-based deep learning framework for the open world class discovery problem, which is a new paradigm. And our method bridges the supervised and unsupervised information to achieve this kind of knowledge transfer, the biggest challenge here. And finally, our method improves the state of the art on 3 benchmark datasets and a real-world radiofrequency dataset by a 2% to 12% margin. So here's the outline today. I'm going to introduce our Class Discovery Kernel Network algorithm, or CD-KNet, followed by the experimental results we have in the paper, and then we conclude by introducing our conclusion and the future works. So first of all, before getting into the details of our method, I want to introduce the Hilbert Schmidt Independence Criterion, which is a very important dependence measure here used in our method. We can call it HSIC. So HSIC is a statistic dependence measure between two random variables. Well, it has the advantage that it could be evaluated empirically over mutual information, which is another normal dependence measure we often use. So in mutual information, we always need to evaluate the joint distribution, which is hard to do so. But for HSIC, it is quite easy. And also, HSIC has been widely applied in feature selection and dimensionality reduction. And HSIC also has close relation to spectral clustering. We'll discussing very quickly. And here's the formula of HSIC. For data matrix P and Q, the exact expression of HSIC is as follows. We need to evaluate the corresponding kernel matrix of the data matrix to calculate HSIC. Often we use Gaussian kernel for input data and the linear kernel for label or cluster embedding. So HSIC has been widely used for supervised setting and unsupervised setting. So in supervised learning setting, maximizing the HSIC between the latent embedding and the labels will give you meaningful feature extractor f theta. So note that f theta is a feature extractor. So f theta x is the feature vector we extracted from the raw input, which is very intuitive. But in the unsupervised learning setting, we need a cluster embedding variable u here to indicate the cluster assignments. But the fact that is in unsupervised learning setting, we don't have any of the label information. Unlike in supervised setting, we have y to perform this role. But here we have a solution to work out. So we kind of initialize the cluster embedding by doing spectral clustering. So maximizing the dependency between f theta of x and the cluster embedding will let our f theta x be as meaningful as we get from spectral clustering. However, here we're doing something more. We're jointly maximizing the HSIC with respect to both of the feature extractor theta as well as the spectral embedding u. So these two variables will kind of push each other to get better performance, so that we finally get a good feature extractor better than spectral embedding. So after we got the knowledge of HSIC, let me introduce you to our Class Discovery Kernel Network. So our CD-KNet algorithm contains 3 stages. The first stage, we call it pre-training. It's just simple process using label data containing old classes. Note that we intentionally decompose the DNN into 2 parts, the softmax layer and the feature extractor f theta. The feature extractor are simply hidden layers of DNN, which may contain convolutional layers or dense layers, and so on. After we got the feature extractor, we can proceed to our second stage. We call it CD-KNet. In this stage, we'll make use of both labeled and unlabeled data. So first of all, we feed the labeled data XL containing only old classes into the feature extractor f theta to get the latent embedding f theta of XL. Then we want to do the normal thing, which is we maximize the HSIC between the latent embedding and the true labels. In this way, we're kind of performing knowledge transfer with supervised information from old classes. This step is very intuitive because we are just doing the supervised learning setting with HSIC. In the second step, for this part, we feed the unlabeled data into the feature extractor as well. However, what is tricky here is that we concatenate the latent embedding from both labeled and unlabeled data together. In this part, we treat both of them as unlabeled. So we will not use the label Y again. But here, similarly, we want to maximize the HSIC between the latent embedding and the cluster embedding U for the whole dataset X. So for now, we can just treat U, as we said before. We can initialize it by using spectral clustering. But here we can simply think about it as it contains the cluster assignments. Now we're doing, by maximizing these HSIC here, we are doing knowledge transfer with unsupervised information from both old and new classes. So this is the whole process. By jointly optimizing these two objectives, we get a refined feature extractor that is suitable for both old and new classes. And then we just get the features from unlabeled data and do simple clustering method to get their new classes assignments. We call it Y-hat. And finally, we got the third stage called expansion. So there are two reasons for doing that. Because we want to mix the labeled and unlabeled data together to achieve further knowledge transfer between old and new classes. And second is that because we kind of want to make open world class discovery process scalable in a lifelong learning process where even more new classes comes and new and different new classes comes, the stage 1, 2, 3 could be repeatable to accommodate different new classes. So in this stage, we use all the data from both old and new classes together to train an expanded network, as now we have cluster assignments as pseudo labels for new classes. So why should we expand the DNN instead? We will not refine the previous neural network, because we need more representational power to accommodate new classes, and our experiments shows the necessity of doing that. So here's our CD-KNet optimization in detail. We're achieving knowledge transfer of combining supervised and unsupervised information together. And here's the formula we have below. Actually, we're just doing a weighted version of the unsupervised and supervised information. Here, you can see that in the left part, we're using both labeled and unlabeled data. This term encourages the separation of latent embedding for all classes, so that both old and new classes should be clusterable in this when we optimize for this objective. And for the right part, we're using only labeled data. It encourages the separation of latent embedding for old classes instructed by the labels we have. In this sense, we're combining the supervised information into the whole objective. So how should we actually optimize for it? We're adopting an alternating optimization strategy that we're optimize the theta via standard stochastic gradient descent, and we're also optimizing U via eigendecomposition. When we optimize theta, we fix U and vice versa. So here comes to our experimental results. So this is a comparison between our method and the baseline method, semi-supervised class discovery, or SSCD. So SSCD is just doing what we elaborated as at the very beginning. They're just pre-training the feature extractor on old classes and directly use it on new classes and perform k-means clustering. So here we also have our unsupervised variation. That is, when doing HSIC optimization, we're just doing the unsupervised part and remove the supervised information part. And the EXP means the method incorporates our network expansion strategy, or stage 3. So here are several conclusions from this table. So first of all, our CD-KNet with expansion beats all the competing methods on different data sets. And you could see that every method adding the expansion strategy performs better than the original version. So actually the expansion strategy in stage 3 helps a lot, actually. Also, adding supervision term, if we compare our variation and our method, actually helps a lot. If we compare the red and blue lines. And also, in order to show that our method actually provides an effective way of incorporating knowledge learned from old classes or the supervised information, we compare our method with 2 state-of-the-art deep learning-based unsupervised clustering methods. So here, to mimic our open world setting, or to mimic the process of incorporating knowledge from old classes, we just pre-train the deep neural nets used in these 2 deep learning method with old classes. And then we perform these algorithms on the new classes. Again, our method CD-KNet with expansion performs better than these 2 deep learning based unsupervised learning algorithms. And also we provide our SNE visualization on the Ioannidis dataset because it's quite easy and clear. So in these 2 pictures, we use the plus sign to represent new classes and the dot to represent old classes. So on the left, we're showing the SNE result using our CD-KNet with expansion. And on the right, we're showing our competing method, SSCD with expansion. So for now, it may be hard to say which one is better, but let me show you this part. So the blue and green, the blue plus and the green dots represents 8 and 3 respectively. And if you notice, like in the red circle, the SSCD is kind of like mixing the 8s and 3s together. So recall that SSCD is just trained on old classes and directly use the feature extractor on new classes. So we can see that it confuses the new and old classes in the embedding space. But our CD-KNet could distinguish them very well. So finally, it comes our conclusion and future work. So in this paper, we propose the open world class discovery kernel network, or CD-KNet method. Our method combines supervised and unsupervised information seamlessly via HSIC. And our method improves state-of-the-art methods on 4 datasets by a 2% to 12% margin. So our future directions include that we may relax the assumption that the test dataset contain only new classes by like integrate this assumption seamlessly in our method instead of doing novelty detection at the very beginning. And also we wanna automatically detect the true number of new classes, which is a very hard problem as well. Okay, that is all for my presentation, and thank you again. Thank you my team, colleagues in Northeastern University, and my advisors. And our code is publicly available in our GitHub repo. Yeah, thank you a lot.